Hello, everyone. Welcome back to the lecture. So now we're going to shift gears and talk a little bit about power regulators and voltage regulators. So this talk is not going to be very comprehensive on the different kind of regulators, but I'm going to talk about a little bit of basics so you can understand how the power conversion actually happens. So let's go back to our original schematic of the power distribution network for a server system. So here you have, as we discussed earlier, there is some, say, some AC input, 110 volts, 60 hertz, and then there's the power adapter, which converts AC to DC. It both steps down the voltage from a high to a lower value and then rectifies it. And then you have the 5-volt DC input, which is sent to the PCB with the power planes. And then you have the dedicated VRMs, which convert the DC value to another DC value, but a lower DC value, called a DC to DC converter. And finally, this voltage is, power is sent to the chip, which has a component called an LDO built in, which helps to further regulate and step down the voltage to finally supply the core circuit of the chip, right? So as we had talked about this, the power conversion is not done in one step, but it is done in multiple steps throughout the power distribution network. And we will talk about how each one of these stages actually operate. If you look at the power that's actually supplied to the PCB, right? One of the questions you might have is why not just start with supplying a low voltage? Why not just supply the core voltage or the voltage required by the chip directly at the PCB side? The reason you don't do this is because you always want to supply the power at an elevated voltage as the PCB input, because supplying power at an elevated voltage would reduce the current for the same value of power. So you can reduce the IR drops as well as the I square R ohmic losses in the conductors when the power is distributed. So generally, you like to send the power at high voltage as possible, and you want to convert that voltage to the lower value of voltage that you need at the chip as close to the chip as possible. So typically, you want to do that final conversion to low voltage at the point of load. And by doing that, you can minimize uh, the IR drop as well as the losses in the power distribution network. So let's look at the server system I showed you before. So now I've actually opened up the power adapter and I've taken this image of the power adapter itself. And you can see that it has multiple elements in it. It basically has a transformer which acts as, which is basically steps down the AC voltage from the 110 volt to lower value, say something like 12 volt or 5 volt. And then it also has a rectifier that rectifies the AC input to a DC, and then a bunch of filter stages that removes the harmonics so that the basically the harmonics are removed, and then you have an almost fixed DC value with minimal ripple or fluctuations. So let's see how this works. So if you look at a typical power adapter, right, it consists of basically a transformer, and then a rectifier unit, and then a filter. So the transformer, as you know, is a magnetic element, and it only works when there's an AC current, because the transformer is based on Faraday's law of induction, and therefore you need a time-varying magnetic field for the transformer to convert voltage from one value to the other. And so here you have a step-down transformer where the output voltage, the ratio of the output to the input voltage is the same as the ratio of the turns of the output to the input. So by reducing the number of turns of the coils at the output here compared to the input, you can reduce the voltage at the output side compared to the input. So you have 110 volt AC applied here. It's stepped down to a lower voltage value. And then you have the rectifier, which is basically a bunch of switches, S1, S2, S3, S4, as shown here, connected in this topology that converts this AC to a single side, basically a single polarity DC. And then that DC, however, as you'll see, has harmonics, and therefore you use a filter stage to remove the harmonics. And then here you get a very stable DC output at around 5 volts. So how does the rectifier work, right? So imagine now you had this AC input at the secondary of the transformer, and during the positive cycle of the AC, S1 and S4 are on, and S2 and S3 are off. So the positive cycle gets connected over here. But during the negative cycle of the AC, S1 and S4 are switched off, but S3 and S2 are switched on. But because the topology is now basically reversed, the reverse polarity is reversed again. And so it ends up showing up as a positive polarity again at the V3 node. So now you have the AC voltage, which is a bunch of positive and negative polarities, converted into a bunch of basically sinusoidal oscillations, but only with a positive, sorry, not sinusoidal, but a bunch of basically increasing and decreasing voltages, but only varying in the positive, basically only varying in the positive polarity, right? So so if you look at the voltage waveforms, so I can plot the voltage waveforms at V1, V2, V3, and finally at the VPCB, which is the load side. And you can see how that looks like. So V1 is basically the high AC 110 volt. And then once it has been stepped down, it reduces to, say, 12 volt or 5 volt, depending on the turns ratio. And then the rectifier itself, by adjusting the way when the switches turn on and off, you can convert this dual polarity sinusoid into a single polarity kind of a waveform that is shown here. And then when this obviously has a average DC value, but also has harmonics in it. And so when you pass it through the LC filter, which is basically a low pass filter, you can remove the harmonics and you end up getting approximately DC value with some voltage ripple. And by designing the filter with a certain value of inductance and a capacitance for the low pass filter, you can essentially design the filter to have a certain cutoff frequency, the 3 dB cutoff frequency, so that you can control the value of ripple within a certain tolerance that you need. So now you have this adapter, this power adapter that's converted the input 110 volt AC now to a lower DC value. So now this DC value is sent through the PCB, and then once it is sent through the PCB, finally before it goes to the chip, has to be converted from that 5 volt DC to a lower DC voltage that is needed for that chip. And how that is done is by using something called as an integrated is something called as a DC to DC converter. And usually there are many ways to do this DC to DC conversion, but the way we are going to talk about here is called as a buck converter. So this would, for example, convert the 5 volt input to say a 2.2 volt DC output, right? And there are also other methods such as switch capacitors, which I won't really go into here. So this is the typical diagram of a buck converter. So the buck converter, this Vin is basically the input, which was the output of the adapter. But now after passing through the PCB power distribution network, it's now come to this DC-DC converter. And it has a bunch of switches here, S1 and S2 connected in this topology. And then it again has an LC filter, a low pass filter connected at the output to remove the harmonics. And this is connected to the load, which in our case would be the actual chip. The buck converter is typically typically a closed loop system. The switching of S1 and S2 is controlled by some PWM controller, which in turn is controlled by an error signal generated by comparing the output voltage at the load to some internal reference voltage. And the reason that is done is because the load is usually not constant, because the chip can consume different kinds of currents. So sometimes it can be there could be a large number of transistors switching, so it draws a high current. Sometimes it's switched off, so it draws no current. So over the entire variation of the load, you need to make sure that the voltage at the load is constant. So you need some kind of closed loop feedback to control the switches. And the basic principle of the buck converter is, if you draw its equivalent circuit, it's basically just the input voltage connected to a bunch of switches S1, S2, as shown here, to the LC filter. So during a certain period called as the on period, T on, S1 is switched on while S2 is off. While during the off period, S1 is off and S2 is on. So what happens when during these periods? So during the on period, which has a time duration of T on, S1 is on, S2 is off, which means the input voltage is connected directly through the load through the LC filter. So the input voltage ends up basically passing a current through the inductor and capacitor, and it basically increases the current that flows through the load. And during the off period, the supply is cut off and the circuit is connected this way. But because the inductor wants to make, inductor cannot have a sudden change in current, the inductor basically makes sure the current flows in the same direction. And during the off period, the current flows in the inductor in the same direction. However, the capacitor current now reverses, and the capacitor charge, this charge stored in the capacitor during the on period, now is used to maintain the voltage at the out. So by doing this and by controlling the ratio of the on time to the total time period of the switching, we can control the amount of voltage that is received at the output compared to the input. Right? So how that can be represented mathematically is the voltage at the output V2 is just going to be the ratio of the on period versus the total time period times the input. So you can see how this is true. Imagine that that it was always on. So if the on period was exactly equal to the time period, then the output should just be the input because S1 will always be connected, and therefore the load will just reach the input voltage. However, if the T on was, say, 50% of the time period, then for 50% of the time, the capacitor is connected to Vn, but the rest of the time, the capacitor is basically discharges. So the voltage at the output, depending on this ratio, is going to be just this T on versus the time period ratio times the input voltage. So how do the waveforms look like? So for example, here you see I plotted the waveforms at the different locations. This is the input at the supply side, V1 and V2, which is the load side. So you see the input is a constant DC, say, for example, at some value V in. V1 is just going to be the switched version of V in. So during the on period, when S1 is on and S2 is off, V1 is just connected to V in. So it's just V in. And during the off period, V1 is just shorted to the ground, therefore it's zero, and then you get this waveform. And therefore V2 during the on period, the value of the voltage is just going to increase because the capacitor is getting charged. And then during the off period, the capacitor is discharging, so the voltage is dropping, and so on. And this is periodic. And therefore, you get some fluctuations of voltage in the output side, which is given by delta V, which is basically the voltage ripple. And similarly, you also have a current ripple because of the fact that during the on period, the capacitor is during the on period, the load is connected to the V in, so the current is going up. But during the off period, the current is basically decaying because the voltage is dropping. And so you get this ripple in the current as well. So just by controlling the value of this so-called duty cycle, you can get any value of voltage at the output between basically anywhere between 0 and Vn, depending on what value of duty cycle you set. And you can also control the value of this voltage ripple and the current ripple at the output by designing your value of the basically the low pass filter, the value of the LNC of the low pass filter. So how basically this low pass filter you would design it? So basically V1 of t. So remember V1 of t is the input voltage as applied to this low pass filter would be basically the step function where it's on for a period t on and off for a period t off. So you can represent this voltage as a basically as a Fourier series with some DC component, which is basically the average value of the voltage here, which is some DC component, plus basically the Fourier components, which basically have some frequency spectrum. And then if you can basically design the value of L and C, and this is basically if you look at circuit theory, right? So during the on period and off period, you can get the value of the current at the output or current through load just by solving these differential equations, which are second order differential equations because of the presence of the inductor and capacitor. And what you'll find is that if you go through this analysis, you'll find that for a given switching frequency omega, and for a given value of the output with respect to the input, which is V out by V in duty cycle, we can design the filter to have a certain minimum capacitance value and a minimum inductance value so that the voltage and the current at the output, the voltage and current fluctuations are within a certain tolerance value. So for example, how this would look is, say you set the output voltage to have less than 5% variation and the output current less than 2% variation. Then what you can do is you can substitute those tolerances within this formula and you can calculate the minimum value of capacitance and inductance to design your filter so that the ripple is basically maintained within those tolerances. So this is how you would actually go ahead and design a buck converter for doing the DC to DC conversion. So if you look from this formula here for the minimum capacitance and inductance, you find that the capacitance and inductance are inversely proportional to the switching frequency. So if here I've plotted the value of the design inductance and capacitance versus the switching frequency, and you see that as the switching frequency increases, basically this is a log scale, so you find that the inductance is dropping and the capacitance is dropping in frequency. So you can see now how we can. Uh, so if you take a typical buck converter, right? The buck converter, the switches in the buck converter are typically very small, and the size of the buck converter is usually dominated by the inductance and capacitance, because inductance and capacitance are typically much more bulkier than the switches. So if you want to have a buck converter as close to the load as possible, which I described earlier has many benefits because having the voltage conversion at point of load reduces the IR drop as well as the losses in the power distribution network. So, in order to have the buck converter as close to the point of load as possible, you want to make it as small as possible. Because imagine you are actually integrating this on chip, so it has to be as small as possible. So the way you would do that is to increase the frequency, switching frequency. However, that can have some negative effects also because increasing the switching frequency increases the losses in the switches and so on. So typically you have to there's a lot of work done in trying to design the buck converter so that you can minimize the switching losses versus the actual size of the buck converter. So this is typically an example of the future where people have been trying to increase this operating frequency of the buck converter so that they can reduce the size of these passive inductors and capacitors that are used so that now you can actually have something called an IVR or an integrated voltage regulator that can be integrated directly into the package or can be integrated directly on chip. And the key to this is actually ends up being the design of the inductor because inductors are very difficult to scale down. So a lot of research is being done to try to incorporate magnetic materials on chip, for example, to reduce the footprint of the inductor and have a very efficient buck converter on chip. Obviously, this is basically what I talked about. On-chip voltage regulators, because of the inefficiencies of the inductor, overall their efficiencies are not good. And so a lot of research is being done to come up with voltage regulators on chip or near the point of load that are more efficient. Finally, as we discussed, so you have the just a little recap. The 110 volt was converted to a 12 volt DC in the step down transformer rectifier stage, which was then sent to the DC-DC converter near the point of load, where it was converted to a lower voltage value. And now finally, the voltage that is sent to the chip goes into another voltage regulator component called as an LDO that finally drops down this voltage or reduces this voltage from the input value to the target output value. Now, the LDO, if you see here, this is a typical topology of the LDO. The LDO is basically just a resistance divider. So it has a switch over here, which is some transistor. And the switching of this transistor is essentially controlled by this gate driver, which takes an input error signal, which is basically the output voltage uh, times some fraction, which depends on the voltage division over here. And that output voltage times some fraction is compared with the reference to generate an error signal, which is used to which is used in the gate driver using a PWM controller to control the switch. And what this basically does is, say you set some target reference voltage, the closed loop control here basically changes the switching of this transistor so that it essentially changes the on resistance, the effective on resistance of this component here, so that you get the output voltage to be equal to the reference voltage. So the LDO itself is basically just a resistance divider where there is a variable resistor here that is controlled actively using this closed loop feedback so that the input voltage can be dropped. Basically, the input voltage can be dropped at this variable resistor to get the output voltage. As you see, because the LDO actually uses a resistive element to reduce to basically drop the voltage from the input to the output, it is much more inefficient than a buck converter that uses basically just switching and passives to do the voltage conversion. And so an LDO is only preferred when the input and the output voltage differential is very small. So for example, and why that is the case is because you see here that the actual current that passes through this is going to depend on this voltage differential because it's just going to be this voltage differential over the value of this resistor, the on resistance of this switch. So if the input and output voltages are very close to each other, this current that flows is very less, and therefore the power lost because of this variable resistor is less. So the LDOs are typically only efficient and are generally used only when the input and the output are very close to each other. But the reason why people like to use LDO on chip is because LDO has a very fast closed loop control, so it's very good to regulate the output and make sure that the output has as minimal fluctuations with respect to load variation. So that's why we typically use an LDO. So I hope you guys got a good understanding of like various kinds of power converters and how they work together to basically convert the power at the input, which is 110 volt, all the way to the circuits which are located on the chip in multiple stages. So, all right, thank you.